Hello everyone, Guy here. Today we're looking at harmonic response, and we're looking at the harmonic response of our truss beam structure when it's subjected to rotating forces. So we want to see what will be the impact of rotating forces on our structure. Without further ado, let's get on the computer and see what we can learn. Hello again. We're looking at the harmonic response of our truss structure when subjected to rotating forces. So let's look at the forces that are applied first. Here are the four forces that are applied in the Z direction. So Z direction is the weak axis bending. And now to get rotating forces, to simulate rotating forces, we're adding four Y direction or vertical forces at the same four nodes, but the big difference here is that we have included a phase angle of 90 degrees compared to the forces in the Z direction, which when you look at the phase angle, they're all at 0 degrees. So that's how you get the rotating aspect, by assigning a 90-degree phase angle. So it means that the vectors in the Y direction are out of phase by 90 degrees compared to the vectors in the Z direction, and that's how you get your rotating forces. Now, what else matters when you do a harmonic response? You need to specify the frequencies of interest. So in this case, I have assigned a minimum frequency of 5 Hertz. So we will first assume that the forces are acting at 5 Hertz up to 75 Hertz, which is the range maximum here, and we'll have 90 solution intervals. So in between 5 and 75 Hertz, we'll have 90 separate frequencies. Very important too, and we'll see that when we look at the response, because our system is low damping, it's important to make sure that we define our own user frequencies, which correspond to the mechanical natural frequency of the structure. So that's what I've done here in this table of 18 rows. I have specified specific frequencies at which I want the solver to solve for the response. So line 1 is 10. It means that we're going to look at the response when the forces are exactly at 10 Hertz. The second line is 10.1. We will get the response at 10.1 Hertz above, over and above the 90 solution intervals that are requested here. It's also here that I specify the damping controls, or the damping value. In the case of interest, I have specified a damping ratio of 0.02 or 2% has been specified. Once we solve, what we can get are two different type of results that we will look at here. First, I'll look at what we call the frequency response. This is for the vertical displacement, so the Y direction displacement at the node where the loads are applied. So that's vertical, that's Z direction or transverse. And what we clearly see here is the amplitude of that node with respect to the different frequencies at which we solved. So we asked for a solution that goes from 5 to 75 Hertz. That's why the x-axis of that plot goes from 5 to 75. And we clearly see the response. As I mentioned before, it's a lightly damped system, so there is a lot of amplification around the resonant frequencies. Here is the first natural frequency around the weak axis at 10 Hertz. Here is number 3, around 36 Hertz. As we saw before, we see that there is a significant response at these frequencies. Now, if we look at the other direction, the vertical direction, in this case, the response is at around 14 Hertz, which you will remember is the first bending mode around the strong axis, as well as around 48 Hertz, which is the second bending mode around the strong axis. And we see that these maximum are well represented in our curve. So we've isolated a sufficient amount of frequencies to represent clearly what the response is. Now let's look at 3 deformation pattern. The first deformation pattern is at 5.6 Hertz. It's actually the first set of results that we solved for. So this is the displacement that we get, the total deformation. And how I like to look at this is by almost being aligned with the x direction, but not quite, as we see here on the screen. So let me just zoom this thing a little bit, and let's animate this. What do we see? We see a motion that's mainly in the z direction along the weak axis, because right now we're below the first natural frequency of 10 Hertz, which occurs around the weak axis, and we're quite far from the first mode around the strong axis, or the first mode in the y direction, which is at 14 Hertz. Now let's look at a second deformation pattern. So in this case, for this first deformation pattern at 5.8 Hertz, we see a motion that's mainly in the z direction. We're now going to move to 15 Hertz, which is slightly above the first mode in the strong axis direction. So this first mode is at 14 Hertz. What we see here is clearly a displacement that's slightly in the z direction, but mainly in the y direction. Now what's interesting, when are we going to see the structure rotates? Because remember that the forces are rotating forces. Well, the best place where you're going to see this is when you pick a frequency that's between the first bending mode around the weak axis and the first bending mode around the strong axis. And in this case, we're looking at the results when the forces are applied at 12 Hertz. And in this case, as you can see, you see the beam rotating because the impact of the rotating forces is really felt at that frequency where we excite both. These forces will excite both the first bending mode around the weak axis at 10 Hertz and the first bending mode around the strong axis, which is at 14 Hertz. So that's it for this example where we've applied rotating forces at x equals L over 4 for our truss beam.